Hey folks, in this video we're going to talk about gravity as a centripetal force. Let's take a look. When the Earth orbits the Sun or the Moon orbits the Earth, gravity provides the centripetal force necessary to keep the objects in circular motion. If we set the centripetal force equal to the force of gravity, we can calculate the object's orbital velocity, its orbital period, meaning the amount of time it takes to complete one orbit, and even the mass of the object. So the big idea here is that the force of gravity is equal to the centripetal force, which of course means that Newton's law of universal gravitation, gm1 m2 over r squared, is now going to be equal to mv squared over r. So in this example in the top right, we have a satellite that's orbiting the Earth, and the satellite has mass, so it would be m1 in the equation. The Earth has mass, so it would be m2 in the equation. And then the distance that it's orbiting away, it's got the circular orbit around the Earth. The distance that it's orbiting away would be r, this radial distance. So let's take a look at example 1. Example 1, Earth's orbit around the Sun. Earth has a mass of 6 times 10 to the 24 kilograms and orbits the Earth at a distance of 1.49 times 10 to the 11th meters. The Sun has a mass of 2 times 10 to the 30th kilograms. The radius of Earth is 6.4 times 10 to the 6th meters. Label this information on the picture below. So I've got the Sun in the middle, I've got the Earth out here, and I've added all these details from the question. So now we're being asked to calculate the force of gravity on Earth from the Sun. So we're going to start with Newton's law of universal gravitation. The force of gravity is g times m1 m2 over r squared. And so I'm just going to plug in the numbers and be careful with my calculator, making sure that I include this square right here, something that a lot of students miss. And I end up getting a huge force, 3.56 times 10 to the 22 newtons. Let's continue on. Question C, calculate the orbital velocity of Earth, meaning its velocity around the Sun. And here's the hint, you will need to set the centripetal force equal to the force of gravity. So that's what I'm going to do here. Remember, that was the main idea of this whole set of examples, is that the force of gravity is the only force acting on the orbiting thing. So it alone is providing the centripetal force. So I'll start here. I already calculated the force of gravity, and then I'm going to set that equal to the centripetal force equation, mv squared over r. Now, a lot of students get confused when they see the mv squared over r about which mass and which radius we're talking about. We're always talking about the mass of the thing that's going in a circle. So in this case, it's the mass of the Earth. And we're always talking about the radius of the circle that the mass is traveling in. So in this case, it would be the radius of that circular path. Plugging in the numbers and solving for v squared, so which means I'll have to do some algebra and then take the square root, I get a velocity of 29,833 meters per second. So think about that for a second. Right now, you are moving around the Sun, because you're on the Earth, at 29,833 meters per second. Why don't you notice that? You're moving incredibly fast. Well, one of the reasons why you don't notice that is because your whole environment is moving at that same speed. The walls around you, the building that you're in, the trees, the ground below. Everything around you is moving at that same speed. So of course you wouldn't realize that you were moving that fast. Next, show that the orbital period of Earth is roughly 365 days. So orbital period is the amount of time it takes to make an orbit, and we call that a year. So what we're going to do is we're going to start by saying that the velocity of Earth as it goes around the Sun is equal to 2 pi r over t. 2 pi r is the circumference of a circle, and velocity is always the distance divided by time. So that's where the 2 pi r, which is the distance divided by time, comes from. We just found the velocity in the previous problem. We're going to set that equal to 2 pi r. This is the Earth to Sun radius, right? That's the radius of the circular path. And then we get a time in seconds because we used a velocity in meters per second. And so we're just going to do some dimensional analysis. Divide by 60, divide by 60, divide by 24. And we get pretty darn close to 365 days. Calculate the acceleration due to gravity on the surface of the Earth. Well, we already know it's going to be 9.8. You've been using that number all year long in physics, but let's see where that comes from. So starting here, we know that for an object that is in free fall, according to Newton's second law, acceleration is force divided by mass. That is Newton's second law. An object that's in free fall is only experiencing one force, so the net force on it is gravity, and then you divide by the mass of the object itself. Well, the force of gravity on any object is always equal to Newton's universal law of gravitation. So the force of gravity by itself is g m1 m2 over r squared. And then we're still going to divide by the mass of the object down here. And so those masses end up canceling. You'll notice here, mass of the object on top cancels with the mass of the object on the bottom. And so we get this really convenient way of expressing the acceleration due to gravity on any planet would always be gm over r squared, where now the radius is the distance between the object and the center of the planet. So now we're going to use the radius from the object to the Earth, and we're going to square that. Plugging in the numbers here, gm1 times the mass of the Earth divided by the radius squared, we get that 9.8 meters per second squared, as we thought. And the meters per second squared, by the way, comes from newtons per kilogram. Finally, if the Earth was suddenly placed 3 times farther away from the sun, what would happen to the force of gravity between them? Well, since the force of gravity is proportional to 1 over distance squared, then if we tripled the distance, we would triple the distance in the denominator, which would be then squared. So we would get a force that's proportional to 1 over 9. Therefore, the force of gravity wouldn't be 3 times weaker, it would actually be 9 times weaker. That's what an inverse square relationship is all about.